Okay, so new section, new topic for today. Well, kind of new. There's actually going to be a lot of really familiar stuff in what we're going to talk about today. We're going to get into section 7.3, and the first theorem that we're going to talk about here in section 7.3, it's a different context, but what you're going to find is that it's structurally really, really similar to Green's theorem. Now, again, different context, different dimension that it happens in, different accumulating quantity that it's in reference to. But structurally, a lot of similarities. Now, I've deliberately laid it out on the page over the next several pages here to look just like Green's theorem, the development that we made of Green's theorem, to emphasize this similarity. And if you recall from our discussion of Green's theorem, hopefully no surprise then, the first thing we're going to talk about is boundaries. Right? Now, so, of course, in the kind of stuff that we're doing here in chapters 6 and 7, we need to talk about oriented boundaries. Right? If we're going to talk about vector line integrals, if we're going to talk about vector surface integrals, these need to be oriented domains. I need to know which way is the correct way. What is the designated proper direction, either along a curve or through a surface? That's what an orientation means. And so, okay, here we are. We're going to entertain the idea of having a solid region R, which I've got shaded in gray, and I'm going to highlight in green here. There's our solid region, a little bit of a weird solid region. It's kind of hollow, if you will, right? It's got a big air gap in the middle of it. Nevertheless, there's a solid region. And the boundary surface, of course, is, it's a surface that I'm trying to draw in space. That's intrinsically hard, but if you'll bear with me, it's, something kind of like that, if you will. All right. Notice the boundary surface has two chunks, right? There's what you might call the outside part of the boundary, what you might call the inside part of the boundary. Okay, so here's the orientation. When we say the word boundary, just like with two-dimensional regions and their boundary curves, the word boundary means an implicit orientation according to a certain rule. The rule, I will confess, is arbitrary, but it's an arbitrary choice like I made 150 years ago, and so at this point it's standard, right? So it's not optional. And here's the rule. Away from the solid is the rule. So now it's relatively easy to think about what that means in reference to, let's say, a point over here on the what we might call the outside part of the boundary. Away from the solid means outward. Sure, right? Pretty intuitive that this is away from the solid. Now, just to clarify, though, I don't want to conflate, even though they coincide in this case, I don't want to conflate away from the solid with outward. Now, the same thing here. But if you were to look at a point on the inside, what you might call the inside part of the boundary, keep in mind the solid is here in green. Right? From this point on the boundary, that's where the solid is. So away from the solid is that way, which is not outward. Right? This very reasonably would probably be called inward. Right? So again, we have an arbitrary but standard convention on orientations. And again, there's kind of two ways to think about it. There's the correct way to think about it, and there's the convenient but not always correct way to think about it. And you got to make sure to always think about it the correct way. So don't make the mistake with, boundary curves to think that it's always counterclockwise. It's not. Right? It's always a rule about move so that the region's on your left. Right? Likewise here, it's tempting to say it's always outward. It's not. It's always away from the solid, though. Okay, how are we doing? Is everybody okay with this arbitrary convention that I claim is highly standard? All right. Okay, the next thing we talked about when we were doing Green's theorem, we talked about accumulation. So we're going to do the same thing here again. Structurally, this is really, really analogous argument. So we're going to go through all the ideas in the same order. Now, a different object in play, different quantity in play. We're not talking about circulation here. Gauss's theorem is about a different quantity, which, as it turns out, also accumulates. So the quantity that we're going to be talking about, boundary flux. Okay, so given a two-dimensional region, right, there's a two-dimensional region. Boundary flux, of course, let's see here. Well, I guess I can use this picture. Boundary flux means, well, obviously we're going to look at the boundary surface, and we're going to talk about flux oriented per the convention through that boundary. All right, so here's a picture in some sense of what boundary flux looks like. Now, just to be repetitive, I'm going to remind you that sometimes people will call this outward boundary flux or outward-oriented boundary flux. That's technically repetitious. Boundary already means outward-oriented. Right? But anyway, just to be clear, sometimes people will say outward boundary flux. Okay, so I claim that this is an accumulating quantity. This is a little bit surprising. It doesn't seem, it kind of at a glance feels like surface area, like it should be related to surface area. Surface area is definitely not accumulating over the interior. That is definitely not the case, right? If you chop something in half, you are creating more surface area. So surface area not an accumulating quantity over a solid. But I claim boundary flux is, and let's see why. Let's look at the left half. If I were to chop this region into, pieces, there's the left half. Boundary flux outward out of the boundary of that region. Keep in mind, we're talking about just this green region R1. So outward on this cut surface, this cut face, outward means that way. Okay. All right. Now, let's look at, here, let me try to go ahead just for emphasis. There we go. Okay, now let's look at the blue region. Looking at this blue region here. Boundary flux, outward oriented, of course. Boundary flux, here's what the boundary of that blue region looks like, and outward oriented, again, per the convention, outward away from the solid. Outward oriented boundary flux is like that. Everybody with me so far? Now, to accumulate, what we would need is for this green boundary flux and this blue boundary flux to add up to the boundary flux for the whole region. This is what the boundary flux would look like for the solid as a whole, right? For that solid as a whole, there's the boundary, there's outward. Are these the same? Is green plus blue equal to purple? Well, in a lot of places they clearly coincide, like on this face here, the green and the purple, it's the exact same thing. Likewise on the, over here on the blue side of things, right? We have the blue and the purple, exactly the same thing, so we cancel that. And all we're left with is just this shared face, sort of the cut face there. And now it does appear that we have a leftover. It looks like there's an incompatibility. The whole is not the sum of the parts, so it seems, because after all, the difference is this, until we realize that, of course, what we have here is two identical computations on the exact same surface, with the only difference being that they are oriented in exactly opposite ways. These two fluxes are negatives of each other, and they cancel, and there is nothing left over, and boundary flux accumulates. Is that cool? Is everybody happy with that? All right. Okay, so big conclusion. Now, by the way, just for kind of comparison purposes, take a look in the notes from section 6.2 when we wrote down the two-dimensional divergence theorem, and I think it was on the very next page, or maybe it was 2 pages after, I forget. But we, after talking about the two-dimensional divergence theorem, I made the observation that two-dimensional boundary flux, namely through the boundary curve, could be thought of as an accumulating quantity, and I drew a picture that was kind of like this. It was, if you will, a two-dimensional version of this picture. So I think it's a really healthy exercise to go back to those pages and do a little compare and contrast in your mind and notice how, it's a really, really equivalent argument that we've made here. Okay. Alrighty, moving along. So I've made the observation before that when you have an accumulating quantity, you can think of it, whatever it actually is, okay, whatever. But you can think of it as being a stuff that is distributed over that interior over which it accumulates. Right? So I'm going to make the case here again that boundary flux, we just got through observing that boundary flux is an accumulating quantity, and I claim again that you can view it as being a stuff distributed over the interior. Now, again, that's straining credulity because it says flux is computed on surfaces. We think of that as being literally, therefore, on the boundary. What do you mean it's coming from the interior? Doesn't seem right. Further exacerbated by the use of the word boundary right there. Again, it seems to be screaming that this is happening on the boundary. But this is semantics. This is red herring. This is a little bit misleading, I would say. Okay, and so I'm going to try to persuade you now that that this thing called boundary flux actually isn't. You can really literally think of it as being distributed over the interior. The way I'm going to do this is I'm going to talk through what we know about boundary flux without saying the word boundary flux. I'm going to make up a different word just so I can talk about it without having to constantly deal with the misleading implications of the term itself. So I'm going to call it blah blah. Right? So let's talk about blah blah. We know blah blah is an accumulating quantity. We know therefore that blah blah for the whole is equal to the sum of the blah blah on that side and the blah blah on this side. So the green blah blah is equal to blue blah blah plus orange blah blah. Now how could that be? I mean, what does that make you think of if the blah blah for the whole is equal to the blue side blah blah plus the orange side? Doesn't it make it feel like it's happening on the interior? That's where it, just like it was mass or population of, mosquitoes flying around in this region or what have you, right? So likewise then, along these same lines, the blah blah for the whole is just the sum of the blah blahs over these little rectangular boxes. If you add up all of these little orange blah blahs, you're going to get the green blah blah. Really makes it seem like the blah blahs in the interior. So algebraically, accumulating quantities can and really ideally should be thought of as happening in the interior. Even though, okay, now back to the actual language at hand, even though where we describe it, where we compute it, might say boundary, but again, that's really not how you should think about it. I hope that might be persuasive. Anyway, punchline, same punchline as before. You can think of boundary flux as being a kind of a stuff, this concrete, kind of material. It's actual stuff. All right. Reminder, we talked about the same thing with respect to previous theorems. Okay. All right. Well, if you've got stuff, then you can talk about stuff per unit volume. Or in general, stuff per unit size. Right? So, all right, fine. Well, this, for example, is mass density. because it says how much, if I can get my thing to work, come on, how much mass stuff in that region per unit size. I said differently, it's what you multiply by size to get stuff, right? The old notion of density, again, this is the most common, this is everybody's sort of first concept of density. Well, modeling on that, let's talk about flux density. And in perfect analogy, flux, now instead of mass being my accumulating quantity, I'm going to look at flux in my region per unit volume. Said differently, this is what you multiply by volume to get flux. So, pretty natural terminology to call this flux density. Perfect analogy with the old familiar concept of mass density. Is that cool? All right. By the way, and I've said this before, but I think it bears repeating. This term flux density, very, very common. I did not make this up. This is not me pushing for some a non-standard point of view on things. It's extremely common, and what we're going to see momentarily is flux density is just that's what divergence is. And with that in mind, we've got now two words for the same thing. One term is flux density, the other term is divergence. You can use either one. And my experience in my physics classes anyway is, back in my past life, I heard this term used by my instructors, flux density, more than I heard this term, divergence. So, very, very common term, and I think it's great. I'm a huge fan of this term, flux density, because that really points at what it is. This conjures this idea of flux as being a stuff, and by pointing to the role that divergence plays in the conversation, which is that it's describing how much of that stuff there is per unit size. It's doing this part of the it's describing anyway this part of the computation. So big fan, flux density, super, all for it. Okay, so it is excuse me, something I'm going to ask you to just take on faith, that flux density actually is this expression, aka divergence, aka those notations that we've talked about long ago. There is a computation that you can do to justify this. It is not an unreasonable computation, but it does take a little time, and it's got details in it, and it, frankly, pretty forgettable computation. It's not that it's not important. It is a very worthwhile computation, but in the big scheme of things, as pressed for time as we are in this course, I think it's far more important for students to understand how divergence is going to be interpreted and how we're going to make connections with it than it is to know where the formula explicitly, that explicit formula itself comes from. So that part of the calculation, how to compute flux density as this formula, don't worry about it. It's in the book. You can look at that if you're curious. It's not even all that bad. But it's not something I am too worried about. Okay. All right. So, now I want to remind you, let's see here. Let me go back to here. This is our chapter 6 notes. Looks like that is page 17 of our chapter 6 notes. I gave you all this point of view on the derivative. If I can get my pen to work. It's the integrand in an accumulation theorem for change. And as such, you can view it as being a density. And as such, it kind of can be used to point to where that stuff is. Namely, change being a stuff, being an accumulating quantity that we view as like a material substance. The derivative is the indication of where that is, or more specifically, how densely distributed, that is, in various different places. And so, for example, if I'm interested in these 2 points, 1 and 2, and I've got this function f here, and it's changing, where's the change happening? Where is there more? Obviously, change doesn't happen at points. Change happens over intervals. Yeah, fine. But loosely speaking, if I ask you where the change is happening, you're going to look at the derivative. You're going to see where the derivative is the greatest, and that's where there's more change happening. Again, pretty intuitively satisfying. Clearly, you can just look at the graph here. There's clearly more change happening at the point 2 than is happening at the point 1. Right? So it's not just that these densities are our integrands. These densities also point to specifically where the total quantity is coming from and how much. And I think that's really valuable, if only for intuition's sake. And then we did this example here, analogous example. If you want to know where the circulation's coming from, look at circulation density, aka Green's operator. And wherever that is the greater, that's the point where more circulation is happening between those two options. And if you're interested in flux, now this is two-dimensional flux here, right? You want to know where the flux is happening? Well, divergence is the flux density. So divergence, whichever one of these divergences is greater, that tells you which point more of the flux is happening. So just like with the derivative, just like with Green's operator. And so now back to three-dimensional divergence. Again, divergence indicates, per unit volume, of course. Divergence indicates where the flux is happening in the interior. And here's an explicit example. I've got a vector field. This vector field creates a flux through the, boundary of some region, whatever, don't even really care. But it creates a boundary flux. Where's that flux coming from? Between these 2 points anyway. Is more of the flux that we observe on the boundary, is more of it coming from A or is more of it coming from B? Well, we just have to look at our flux density, aka divergence. We plug in these 2 points and we see where the divergence is greater. Give me 1 second. The divergence is greater at the point B, and so therefore the point B is where more of the flux is coming from. Yeah?
Does the ball and the size of the ball have any significance from this?
Not particularly. I mean, what I'm pointing to in this example is what I'm going to call a local interpretation of divergence. What does divergence say about what's happening in a teeny tiny little region, right? And so going back to this example here, in reference to the fundamental theorem of calculus, it doesn't really matter that we're looking at the interval from 0 to 3, particularly. If I can ask the question completely independent of this interval, I can say, is there more change happening at this point 2, or is there more change happening at this point 1? It remains that change density is higher here and less here, right? So it remains there's more change happening at 2 than at 1. It doesn't really matter what total I'm thinking of that as being a part of. Does that make sense?
Yeah.
Yeah. Anybody else? Good question. Anybody else? All right. Okay, so we have everything we need to make our boundary theorem now. I've called them different things over different times. So accumulation theorem, density theorem, boundary theorem, all of these theorems that we're building up here, they all involve an accumulating quantity. They all involve an integral of a resulting density, and they all happen on a region and its boundary. So sometimes I call these accumulation theorems, sometimes I call them density theorems, sometimes I call them boundary theorems. It kind of depends on my mood. In all cases, I'm referring to the same theorems. So here we go. We talked about flux as being a quantity of interest. It's got a name. It's got a notation, a letter for it. Keep in mind in this context, when we say flux, we do mean boundary flux. That's important. So boundary flux is an accumulating quantity, the whole of the sum of the parts. The boundary flux for a whole solid is just a sum. That's all this triple integral symbol here means is, add up, and then this d phi says all the boundary fluxes for all the little pieces that you've chopped your solid up into. Right? So whole is the sum of the parts is all this says, because it's an accumulating quantity. And then lastly, we have our density observation here, that there is a formula and a notation and a terminology for how much flux per unit volume there is at a given point. And as we just got through emphasizing, divergence is that density. Divergence is flux density. So, all right, now that's the argument we made, but now look at the nice punchline, the pretty unexpected punchline. This is a vector surface integral. And what we see here is that it can be computed with a triple integral of divergence over the corresponding interior. So, there you go. This is called Gauss's divergence theorem. Let me pause before I show you an example. Is everybody on board? Is everybody with me? Okay. All right, now, there's a catch. Reminder, all of these theorems, there is a catch. There's some sort of a corresponding catch. In any one of these accumulation theorems, there's an asterisk. Okay, it only applies if a certain very significant condition holds. Make sure that you know what those conditions, those asterisks are for all of these boundary theorems. Oh, okay, there I did it again. All of the accumulation theorems. Here, the catch is, if you want to compute a flux, the catch is that your surface has to be a boundary. Right? That's the deal. If your surface is not a boundary, then there is no theorem. Everything that we've done in developing this theorem has been with the understanding that flux, as we've referred to it here, is boundary flux, right? So boundaries is the only thing we've been talking about, and it doesn't work if you're not talking about a boundary. And in fact, if you think about it, not only would the theorem not be true, but if your the domain for your flux isn't a boundary, then there is no solid over which to do a triple integral. Like, the whole point to this R is it needs to be the solid whose boundary is your surface. If your surface isn't a boundary at all, there is no R at all. There is no triple integral. It's not that there's a triple integral that is not equal to the flux. No, there is no triple integral. The whole thing is hands up in the air. I don't know what we're talking about. Okay, so that's a big catch. Make sure if you want to use the divergence theorem, make sure, extra sure, that you're talking about a flux through a boundary. Okay, and that's a good segue into our example here. Example here asks us to compute a flux. We've got a surface given. We've got a vector field given. Compute the flux. Okay, fine. All right, well, let's think about that asterisk. Can I compute this with the divergence theorem? First thing I have to establish is whether this surface, let me highlight it, this surface here, is that surface a boundary? Sadly, it's not. It's just not, right? It says right here, inward oriented. And if you think about okay, here we go. If you think about the sphere, that surface there, oriented inward, it's just not a boundary. Keep in mind this word boundary. In chapter 6 and 7, the word boundary is a loaded word. Importantly loaded. Orientation is part of what it means. Boundary means oriented away from the solid. Usually that means outward. In this case, it means outward. But oriented a certain way. And this thing we were given is not. So you cannot apply the divergence theorem directly to this given surface S. Can't do it. Everybody see what I'm saying there? Everybody see the problem? Okay. Please be really careful about that. You can get into big trouble computationally if you start applying the divergence theorem when it doesn't apply, when the thing that you're computing the flux over is not a boundary. Big problems can come out. Okay, so what are we going to do? Well, what we're going to do is recognize that there is a closely related surface, same underlying surface, just oriented the opposite way, that is a boundary. Right? What I'm going to call S minus, per the book's previous notation. S minus here is, it's the sphere containing the ball, and it's oriented outward away from the ball, and it's a boundary. No problem. Specifically, it's the boundary of our ball B here. Okay, so the blue surface is the boundary. Is everybody happy with that? Okay, so fine. It remains, I was asked to compute the green flux, but now I'm talking about the blue flux, and am I allowed to just change the question like that? Well, no, of course not. But what I can do is observe that this relationship between S and S minus, they're the same underlying surface with opposite orientations, and so the flux through one is the negative of the flux through the other. So what I've done here now is I've connected the question that I was initially asked, namely to compute the flux through S. Let me get the colors going on that. The flux through the originally asked green surface, I've connected it to the preferable, much easier to work with, flux through the blue S minus boundary surface. Okay. And the cost of that, of course, is a minus sign, and don't forget your minus sign. That's important. But and side note, again, this is really significantly important. Don't think of every minus sign as all having sort of the same sort of, from a grading point of view, all having the same value, because they're not. If you make a sign error of the sort where, you had three minus signs and somehow you canceled all three of them and got plus, you counted wrong. It happens to the best. That doesn't point to a lack of understanding of a significant point, right? This minus sign comes out of one of the important conceptual tools that we're using in this course, and it is actually really important. So that minus sign alone would be worth several points on an exam question. So do be careful, please, with your orientations. Okay, now all of that said, let's proceed. We just got through talking about how the blue surface is the boundary. So that's worth noting. S minus is the boundary of B. And once I have that it is a boundary, now we're in business. Now we can use Gauss's divergence theorem. This integral is this integral. This flux is this triple integral of divergence because my surface here is a boundary. How are we doing? Everybody all right? All right. Good news. Divergence is easy to compute. The divergence is just 3 plus x. You can see it directly from the vector field. Keep in mind the way that we compute divergence. Back up here, right? We've got this formula: x partial of the first component, y partial of the second, z partial of the third, and so that gives me x partial of this gives me 3, y partial of this gives me x. Z partial of this, there are no z's in there. The z partial of that gives me 0. And so my divergence turns out to be really, really nice. Okay, now last thing is the resulting question of how do I compute that integral? And what can I do with that integrand 3 plus x? It doesn't have any nice odd symmetries. It's not a constant. You could brute force this. You could, spherical coordinates. I mean, our domain here, after all, this domain, my solid, is pretty nice in spherical coordinates. And you could do that, but you're going to end up with some trig because, rho squared sine phi and all that. The x has got some sines and cosines in it as well. So you could do that. But here's a neat trick. I want everybody to be on the lookout for this. This is really useful here and there. When your integrand isn't nice, be open to the possibility it might be made up out of separate terms that are nice. Right? And so I can turn this integral into the sum of that integral plus that integral, and individually these integrands are awesome. 3 is a constant. Right? Just this integral here is just 3 times the volume. Easy. Boom. Geometry problem. This integrand's awesome for a different reason. The integrand is x. It has an odd symmetry over a plane, which is also a plane of symmetry of our ball. That integral is 0 by symmetry. I want y'all to think through these details. Right? Leaving that as an exercise for y'all. We spent a lot of time talking about how to use symmetry. Make sure that you understand all those details. Nice punchline, though. The answer is just basically an easy geometry argument. And there you go. Everybody happy? Cool. Okay, let's talk about some physical examples. By the way, the applications of Gauss's divergence theorem are massive. I know a lot of y'all are engineers, and I know that a lot of you aren't, and apologies, but this is a very engineering-oriented course because of the vast numbers of engineers in this class. And related to that, I have one time on my own asked some engineering professors, hey, what's important to y'all about multivariable calculus? Give me your top 3 most important topics to make sure that we cover in multivariable calculus, right? And they gave me the real estate, the real estate joke about what's the 3 most important things in real estate. The answers are location, location, and location. Right? So they gave me the same answer. Vector calculus theorems of Gauss and Stokes, vector calculus theorems of Gauss and Stokes, and vector calculus theorems of Gauss and Stokes. It's just huge, right? There's so much in this physical world that we live in and that engineers work with that is really very well modeled by the divergence theorem. So here are a couple of examples. I think these are particularly nice. I'm going to start with the light bulb example. Imagine you have a light bulb. I used to have to talk about the filament in the light bulb. It's kind of not really a thing anymore. Now we've got little LEDs, right? The little cube there that the light comes out of. But anyway, there's a point light source in the middle of your light bulb. Okay. Now, what does a light bulb do? Well, it generates photons, which are a bunch of little tiny little particles that all kind of flow outward away from that light bulb. So teeny tiny little particles all flowing together, that's what a fluid is. Right? And it's tempting to say, no, fluids are like a continuous thing, but no, they're not. Right? If you water, for example, it's made up of a bunch of teeny tiny little particles. This is a fluid. And here's for example, the fluid that we create. So, yeah. Outward, of course. A little uncomfortable that these arrows aren't all the same magnitude. Speed of light's a constant. All the photons are flowing at the same velocity. Why are these farther away arrows shorter than these closer in arrows? Simple answer there, and that's keep in mind, vector fields do not always represent velocity. Sometimes, this being a case in point, The vector field represents density times velocity. So even though the velocity is constant, when you're closer into the light bulb, the photons that have just come out of there, they're all kind of close together. And so there's a lot of density. Density is higher near the bulb itself. And then as you get way farther away, well, those photons have had a chance to kind of spread out as you've gotten further away from the bulb, and the density of photons is just lower the farther you go out. Does that make sense to everybody? Another way to say this is that when a light bulb is farther away, it doesn't look as bright. And it's because there's literally not as many photons hitting your eyeball. Okay. All right. Okay, so we've got a flow of a fluid. I want to point out that the fluid flow has certain physical realities. The fluid is being generated by the light bulb. Not all fluids are just being spontaneously generated in your story, right? If you're studying water, most of the time, water is not being created. It's just you've got a certain amount of water in your fish tank. Usually you're not adding water to the fish tank, right? You can still be interested in how that fluid flows. So here, the not always the case point of interest is that the fluid is being generated. But another important point of interest, the density is constant. Whatever however many photons per cubic centimeter you have right here, wait 5 seconds, number of photons per cubic centimeter in that same location, same. We're not collecting photons. As we're generating tons and tons of photons, but we're not sort of collecting more and more, and eventually the whole world will be nothing but just a solid block of photons, right? It does not happen. Does that make sense? All right. Okay, so let's talk about this. Let's talk about this sphere here. And I'll orient the sphere. There we go. Outward oriented sphere. And I could reasonably ask what the flux is through that sphere. And it gives you some value, right? Depends on how many watts your bulb is. But now I want to ask the related question, okay, cool, we got a certain amount of flux. Where'd that flux come from? What's the origin of that flux? Now, let's rewind real quick before we answer that question and go back to, here, and I was laboriously trying to make you believe that flux, we compute it on the boundary, but that's not where it came from, right? And that whole speech I won't repeat. But it's a little bit of a stretch to make yourself believe that it's actually coming from the interior, even though it's measured on the boundary. But now let's think about this example. If I ask, where does the flux come from on the boundary? Oh, no question. It comes from the hot spot. It comes from the LED. Of course that's where it came from. That's where the photons all came from. That's just an immediate thing, right? So now I'm going to claim, without computations, because I don't want to get bogged down in a bunch of algebra, if you were to compute the divergence, if you were to compute the divergence where the LED is, you would find that on and within the LED itself, the divergence is massive. That's pointing for you. It's telling you where the light is coming from. Yeah, we measure it on the boundary. Yeah, fine, of course we do. But that's not where it comes from. It comes from the hot spot. It comes from where the divergence is. The divergence tells you where it comes from. Okay, now by comparison, let's think about a point over here. And let's ask, how much of the flux that I'm measuring on the boundary comes from there? This region, this little, vicinity of some point, kind of off center there, where there's nothing, right? There's just vacuum there. How many of the photons are coming from there? None, right? There's no photons coming from there because there's no light bulb there. right? And as such, if you do the computation, compute the divergence, you get 0. Now, I emphasize there will be photons passing through there, sure. And so as such, there are some photons coming out of that region. But those photons that are coming out of that region, a billionth of a second prior, entered into that region from somewhere else, right? So in other words, none of the photons, even the ones that are passing through this region, none of them came from that region. So don't get lost in thinking about, oh yeah, but there's lots of photons here. Yeah, they're all transients. They're all just passing through. Does that make sense? Okay. All right. Okay, so as previously claimed, and I really like this physical example because of how persuasive it is that divergence is telling you where the boundary flux was coming from. I mean, very, very physically relatable. We see that, as claimed, divergence tells you where flux came from versus where it didn't. Okay. All right, next example. This is a little bit of a weird example also. Different kind of a fluid. I'm going to imagine a balloon, a large balloon. Let's make it a red balloon. How about that? Here's a large balloon. Certain amount of gas inside of the balloon. And let's suppose then that my balloon starts to get bigger and bigger and bigger, right? And so maybe somebody turns up the heat and the balloon expands, whatever. And I appeal to your intuition. As the balloon gets bigger, the gas on the inside has to kind of flow outward along with the balloon. And I claim that the resulting flow of gas particles would be about like this. So it's larger the farther you are away from the center, and it's smaller the closer you are to the center. If you think about it, the point in the exact middle doesn't move at all. Any little piece of gas that's right there, it just kind of sits there, right? Yeah. Anyway, I hope that's reasonably believable, but I'm going to claim that is in fact what happens. Okay, now the question. Oh, I got ahead of myself. Different kind of a fluid. Now again, we have a fluid flowing. It's a gas fluid instead of a photon fluid. Big difference though. The density of gas is changing. The density of gas is not constant. It's getting smaller and smaller. The bigger the balloon gets, the less dense the gas is on the inside. And by contrast, right? Think back to the photon fluid example we just talked about. With photons, the density doesn't change at all. This is a very different kind of a fluid than the photon fluid. By comparison, with this gas inside of a balloon example, we're not making or destroying any gas. The gas involved is limited. It is what it is. We have exactly a certain amount of gas. Again, by contrast, not so with the photon fluid. We're literally generating fluid there, right? So these are two very, very different examples, and because it's a very different kind of a fluid, the modeling by way of the divergence theorem is going to make a different interpretation. Okay, so that in mind, let's think about a sphere. This is a sphere well inside of our balloon. Keep in mind the red balloon. Here's the red balloon here. As the red balloon expands, I want to talk about the flux through this purple sphere. The purple sphere is fixed. It's not changing in size. It's remaining, I don't know, maybe it's a unit sphere or something like that. Okay, so we can write down the divergence theorem. Right. And I can compute the divergence, by the way, a little computation, no big deal, the divergence of that vector field. Make sure you can do this. You take the divergence of that vector field, you get 3k, whatever k is. You don't need to worry about the constants. Make sure you're good to compute that. Think through the details. Ask me in office hours if you're not sure. Okay, so what does this tell us then? What does it mean to say that the flux is equal to the triple integral of this constant? And, the flux is measuring how much mass is leaving outside of this purple sphere, right? As my balloon keeps getting bigger and bigger, the gas is kind of following along with it. And you can see there's literally going to be gas leaving my balloon. So the amount of mass inside of the balloon is decreasing. It's moving into this region over here that keeps getting larger and larger. And so what does the divergence mean in this case? What does this mean? The fact that it's constant, what does that mean? Well, divergence is again telling you where all this mass loss is coming from. Right? We know we're losing mass. You can see the mass leaving out through our purple sphere. There's less and less mass remaining on the inside. Where has that mass come from? If there's less mass, then it's going to be less density throughout the thing. And this 3K here, this constant value of divergence, is telling you how fast the density is decreasing everywhere on the inside. And by virtue of it being constant, that tells you that the density is the rate of decrease of the density inside of here is the same. The density is dropping at the same rate everywhere on the inside, which if you think about it kind of stands to reason because, you can't have a denser region and a less dense region. If you're talking about gas, it would equalize, right? It would move from the high density to the low. The gases spread out and uniformize. Okay. So different interpretations, very different interpretations between these two examples. Different sort of ways in which the divergence theorem kind of overlays on top of these scenarios. But in both cases, the divergence theorem tells you something really useful and natural about the story. Oh, I'm sorry. I just now realized I went over time. Okay, sorry about that. We'll draw the line right there. We'll pick up here on Monday. Y'all have a great weekend, and see you Monday.